Okay, now we're talking about nuclear magnetic resonance here. We're talking about a nuclear property. So how can we from a nuclear property deduce chemical information? And the question is, how does chemical environment influence the nuclear magnetic resonance effect? So let's start out with the nucleus of the proton of the hydrogen atom H1. That's the proton. That's a single lone proton. This proton, typically, if we take an isolated hydrogen atom, is surrounded by an electron. So there's an electron cloud surrounding that nucleus here, and it's nice and symmetric. For the resonance frequency of the pure proton, that is the precession frequency, we have the Larmor frequency, which is gamma B0. So that is the Larmor frequency that we have dealt with so far. Now, if we have our hydrogen atom in a magnetic field, B0, what now happens is a distortion, a very small distortion of the electron cloud. I will not go into the details of the quantum mechanical explanation of how this electron cloud is distorted, but you can rationalize this simply by the fact that the electron which swirls around the nucleus, around the proton, that electron, its flight pattern, is most likely influenced by the presence of an external magnetic field. You can think of it this way: if it happens to fly parallel to B0, there's no influence of the magnetic field. If it flies perpendicular to B0, there's a maximal influence. What the consequence of this is that the electron cloud is deformed, changes ever so slightly its shape. As a result of that, a small magnetic field due to the electron is being introduced. This magnetic field, we will call it here delta B. This magnetic field is proportional to B0 with a proportionality constant delta here. So the presence of the electron around the nucleus in the magnetic field leads to an alteration of the magnetic field at the site of the nucleus. So this small change in the magnetic field B0 at the position of the proton leads to a modified expression for the precession. Here's the Larmor equation, and now we don't have gamma B0, but we have gamma times 1 plus delta. That is the equation of motion that describes the behavior of the magnetization. And as a consequence, the Larmor frequency is now not the precession frequency, which is gamma B0 times this, is now changed, and it is given by the Larmor frequency times 1 plus delta. And this delta is called the chemical shift, short for chemical shift of the Larmor frequency. The sign here is not important for the further understanding, whether we put a plus delta or minus delta. What is important here is that based on the presence of the electron, the proton magnetization will no longer precess exactly at the Larmor frequency. Now let's think about if we have this hydrogen atom close to a nearby electronegative atom, such as oxygen or chlorine. These electronegative atoms attract the electrons. They produce, therefore, a reduced electron density at the site of the proton, and therefore a so-called de-shielding of the nearby hydrogen nuclei of the protons. That means we have less of an effect of the electrons on the resonance frequency. So I'll illustrate this here with an example. First we'll take the normal isolated hydrogen atom. Here's the hydrogen electron. Everything is as we have described here. If we now have nearby an oxygen, so we'll look at a hydrogen nucleus in a OH, which is part of an OH bond, we have the electronegative oxygen, and now for convenience I have drawn a simplified distribution of the electron cloud that belongs to the hydrogen atom. And essentially, because oxygen is electronegative, the probability that the electron is swirling around the hydrogen is much reduced, and most of the electron is actually at the site of the oxygen. So what this means now is if we put the OH group into a magnetic field, there's little shielding from the electron, so there's little modification of the magnetic field at the site of the nucleus of the hydrogen atom here at the proton. Consider a third example. This is a CH bond. So we have the carbon here. Carbon is less electronegative, so it starts to pull the electron cloud of the hydrogen electron over to it, but not as much as the OH, which is here. And so as a result, there is a stronger effect of the presence of the electron on the change in magnetic field. So there's more shielding and a stronger shielding of the magnetic field. This delta B is bigger. So as a consequence, the resonance frequency of the nucleus of the hydrogen atom, of the proton, is higher in an OH bond than it is in a CH bond. So I'll stick with this qualitative description because it helps us qualitatively understand what's happening. The strictly quantum mechanical ab initio calculations trying to predict based on molecular structure of chemical shifts, they are qualitatively very good, but they are not sufficient in explaining all the details that one sees. So we will stick with this qualitative argument here that electronegativity, that is the distribution of the electron clouds, has an influence on the resonance frequency, and therefore through the change in resonance frequency with this nuclear magnetic resonance effect, one is able to sense the chemical environment. So how is this chemical shift of the resonance frequency, or short chemical shift delta, linked to electronegativity? And I've taken here a table. We're looking at compounds CH3X, where X is fluorine, oxygen, chloride, bromine, iodine, hydrogen, or silicon. In these molecules, one has determined the electronegativity precisely, and also the chemical shift of the proton resonance frequency. Taking this table and plotting electronegativity on the x-axis versus the chemical shift on the y-axis, we actually see a fairly nice, at least monotonous relationship between electronegativity and chemical shift. This compound is a little bit different from the others, but this is a very nice, strong correlation between chemical shift and electronegativity. Now, chemical shift is not measured in Hertz, but it's measured in parts per million. And parts per million here is not a measure of the number of molecules present, and it's not an absolute measure. It's actually measured with respect to a reference compound. For proton, tetramethylsilane is one compound, or TMS, and here it is the reference compound, so this is set to 0. So the exact expression here is the difference of the resonance frequency observed relative to that of the reference compound, divided by the frequency of the reference compound, and that typically gives us numbers that are 10 to the minus 6, so it's a parts per million effect, a millionth effect, and so one multiplies by 10 to the 6 to obtain a number which is something on the order of 1 to 10 or something like that. It's easier to write instead of constantly having to write 10 to the minus 6. And that's why it's parts per million, or ppm, because we multiply here by 10 to the 6. So there is no absolute measure here. That this is 0 is a convention. Where the 0 is placed, what is important here is the relative relationship. And so if one looks at the chemical shift of protons, that's the nuclei of hydrogen, in all sorts of different compounds, one knows roughly based on the type of chemical bond in which range the chemical shifts to appear. So we will not see this type OOH with a chemical shift over here. This has a high chemical shift here. This is always with respect to TMS, tetramethylsilane. So this, at what place in the spectrum here, the proton spectrum, the frequency is observed, tells us a lot already about the chemical compound under investigation.